All right, hello everybody. Welcome back to Data Analysis, and congratulations. If you are watching this lecture, you have made it to the end of the course. So this is the final lecture, and so pat yourselves on the back. Today we're going to have a fun lecture. It's going to be a little bit in a different direction than the linear regression we've been doing, but we have the skills to do it, and it's a neat topic. And so I like to introduce it just as a way to get you thinking about advanced topics in a way to, as we conclude the course. And that is, we're going to introduce neural networks today. And so it's trendy, and there's a lot of hype around neural networks. A lot of it is justified, and we will introduce those tools today. It'll be in a limited context, of course, because I only have one lecture to do it in. But again, I think it's nice to put your mind on some advanced topics as you head out of the course. So this topic is not found in either one of our primary course texts, and so yeah, so tough luck if you want to dig a little deeper. Send me an email and I can send you some other references. I will make a disclaimer here, which is that we're only going to be discussing neural networks in the context of regression. Oops, as we sort of fits in with what we've been talking about. So we're only going to be talking about regression today. Neural networks can be used for classification very much in a way similar to how we talked about logistic regression, the idea that we apply this sigmoid function to the output of linear regression in order to get logistic regression and do binary classification. You can do this for neural networks to do binary classification, but we're not going to discuss it today. You can also have multi-label or multi-category output or multi-label output, so not just binary classification. But we're not going to discuss this today. Usually, you would say something about this in an introductory discussion of neural networks, but I want to plug into the things we know best, which is regression, and so we're only going to be talking about these applications. So start us off with a little joke here. If you've watched any Star Trek, which I have, I'm a self-professed Star Trek nerd. In the Next Generation, you'll notice Lieutenant Commander Data here was an android. This is part of the narrative, and he talks about in that show every once in a while he'll have some sort of malfunction and he'll refer to his neural net, talking about sort of this positronic brain and his neural net, and it sounds like a piece of science fiction. And well, the Next Generation, this Star Trek series was recorded in the late 80s. Why is Data talking about neural networks if we have the impression that they're a modern tool, right? And the fact is actually that neural networks have been around since the late 80s, but because of hardware limitations and also because of well, just the way the field went at the time, there's you can talk about why, but they weren't used practically really until starting in 2012. And people preferred other tools. People didn't know that they had the potential that they actually have. But they've been around for a very long time, and they've had some advocates over that time. And some of the people who were the longest, the most dedicated advocates of neural networks are now sort of looking at the success that they have had, and sort of, I think, saying, I told you so. But anyway, so Lieutenant Commander Data has some neural networks, and that being that this class is called Data Analysis, I thought it was appropriate to just mention him in context. Okay, another disclaimer. So neural networks are, I think, very trendy, and it's important to be able to separate when something is trendy. You know, how much of the discussion is hype and how much of it is real substance. Some of the throw a neural network at a problem, in my opinion, is just hype. Sometimes people will, have a hammer that is a neural network, and every problem they come across looks like a nail. They're appropriate for some problems and less appropriate for other problems. I will just highlight some of the areas in which they've had a lot of success, and this is particular computer vision applications. There really is no other tool for image classification in particular where neural networks, there's no other tool like neural networks, and the performance that they bring to this domain is very, very impressive. Reinforcement learning, This is, for example, maybe you've seen about these examples where you like where you teach a neural network to play like a video game or play Go. This is an example of reinforcement learning, which is a Markov decision process. Um, Neural networks have had a lot of success there. Some other examples: uh, natural language processing has been a very big one. This is just uh, um, interpreting uh, writing, right? So that's been another one where neural networks have had a lot of success. So there's some application areas where, if you are working with a problem in these areas, you should know that neural networks are state of the art in this area. Um, in my personal experience, I'll just add this because I have some experience here, and that is that um, sponsors tend to like neural networks more than linear models, and I don't know if it's just because people feel like if they're doing machine learning, they're doing something more advanced and can justify spending money on something. I have no idea, but even when the performance gain between using a neural network and using something simpler is marginal, my experience has been that sponsors like to, and I don't know why. Maybe it's just the trend, but uh, since you can use neural networks for regression tasks, it's worth just sort of introducing them now, like we are, just as a point of comparison to linear models. Um, they are extensions of linear models, and so some of the tools we have will apply, although many tools that we have won't apply. So let's introduce some background and some notation. So I'm going to let AL through A1. This is some L is some non-negative integer here. So AL through A1, they're a collection of conformable matrices. So when I say they're conformable, what that means is that this matrix product here is a valid matrix multiply. So the conformable means these have the appropriate shapes so that this matrix multiply is allowed. Okay? So we have L conformable matrices. And I'm going to assume that A1 here has P columns, where P is the number of predictors, and that AL is a row vector. Okay, so what this allows me to do is when I multiply all these together, this output, if A1 has P columns, so that is A1 is question mark, whatever, it's how many rows it has by P, and then AL is a row vector, okay, by a row vector, right, what that means is it has one vector, one row, and then we don't know how many columns. If I do this matrix multiply, the result is that this is 1 by P. Okay, so that's going to be my assumption on A1 and AL. The shape of this output is important. And then I'm going to introduce a function sigma. So oftentimes in stats, the sigma represents standard deviation. Here, sigma is a function. This is more common notation in machine learning. And so sigma is a function which operates pointwise on matrices. So what that means is that if I give a matrix, if I input a matrix as an argument into this function, what it does is it applies the function element-wise to the matrix. Okay, so it's a matrix which I plug in a matrix, or excuse me, it's a function which I plug in a matrix and it applies an operation element-wise. Okay, so a common example of this function is called the rectified linear unit, ReLU. What it does is you feed in x, an input x. It takes the maximum between x and 0. Okay, so the way we extend this to operate on matrices is that you apply this to a matrix, and it takes the entry-wise maximum between each entry of the matrix and 0. Okay, so if the entry is bigger than 0, it stays. If it's less than 0, the entry becomes 0. Okay. So this is an example of one of these sigma functions, which is called, well, I should mention it somewhere, but the sigma is called an activation function. And I believe that's coming up, but just so we have it here. So sigma is an activation function. It's important that it is nonlinear. Okay, so now let's introduce with that vocabulary. We'll introduce what is a neural network. So in linear regression, we have that the conditional mean of y given some predictor variables is x transpose beta. So that is the conditional mean between y and x is a linear function. And throwback to the very beginning of class, and I hope that you're tracking this, but the name of the game is to estimate these beta coefficients given that the conditional mean is a linear function of x. And in a neural network, what happens is that the conditional mean of y given x is, instead of being a linear function of x and beta, it is a linear function, or excuse me, it is a sequence of compositions. And so what happens is we have the original predictors, okay? They're multiplied by this matrix A1, and then we apply the sigma function. So we have this output, we apply the sigma function, and the sigma function applies this nonlinearity. This is that activation function. And then the output of that, we apply A2, then we apply the sigma function again, and so on and so forth. And so what's happening is we have this sequence of iterations where we are applying a matrix, applying the activation function. Okay, and remember, this thing operates element-wise on matrices, and so we can input the output of this vector or matrix, and we'll operate element-wise on its coordinates here. Okay, and so this is the structure of the conditional mean of y given x, is that it's not linear, it's almost linear in the sense that we have these linear operations, but we have this little bit of nonlinearity here in between each application of the matrix. We have some nonlinearity, and this makes a neural network nonlinear, okay, because of this nonlinearity. If we were to remove these activation function applications, then we would have expected value of y given x is a string of matrix multiplies. We could collapse the matrix multiply into something which would be just estimating beta, just multiplying all those pieces together. It would be a single, we can combine it into a single linear operation. But the fact that we have this activation function means that a neural network is nonlinear. So in linear regression, when the name of the game is to estimate this beta, in a neural network, we want to estimate the values in these different matrices. Okay? So there's a lot more to estimate, and we have some nonlinearity. So a neural network, I say just like here, that's a little bit of an exaggeration, but it's very similar in the sense that we do have this sequence of linear transformations. So a neural network, we have a sequence of linear transformations instead of just a single linear transformation. But the big exception, again, is that this application of this activation function, this nonlinear function in here, makes the relationship between x and the conditional mean nonlinear. Okay, and here is this vocabulary word which I mentioned on the previous slide. This nonlinearity is called the activation function. In general, right, you can be a little more exotic in the sense that you don't have to have the same nonlinear function at every layer. Oftentimes people do, but you could imagine changing this nonlinear function so that it's slightly different between layers. The big advantage of neural networks is that they are simple in certain ways, in the sense that we are composing this linear operation, with the simple nonlinear function, but they're also flexible in certain ways because we are, again, no longer in the world of linear models. So we have a flexibility in that we're working with something nonlinear, but simple in the sense that it's kind of similar. It's similar to being linear, right? We have some trends that emerge and some operations we can take advantage of because of it is almost linearity. It's almost linear except for these iterations in between of the activation function. Okay. Some terminology here. L, that's the number of matrices A here. L is referred to the number of layers in the network. That's what this L stands for. So each of the matrices A is referred to as a layer, though obviously when we actually apply it, so we compose it with this activation function. If L is equal to 1, then the neural network is just a linear model. Okay, if L is equal to 1, that is, we are only applying this AL. We have AL applied to some X. We have just a linear model. Okay. If L is greater than 1, then all the layers but the last layer are called hidden layers. So the reason for this is that, well, what happens is these hidden layers, these intermediate layers, they perform an operation and then pass some output to the next layer, right? And we don't observe these variables in practice the way that we observe our inputs and our outputs, and for that reason they're called hidden layers. If you have a single hidden layer, your network is called shallow. Okay, so you have one intermediate matrix multiply, so you have one activation function, linear multiply, or excuse me, matrix multiply in there. And if you have more than one hidden layers, your neural network is called deep. And so if you are fitting deep neural networks, that is networks with multiple hidden layers, you are doing deep learning. Okay, so another trendy word here, deep learning. But what it means is that we are fitting these models, which have the sequence of linear operations, where of course we have the implication is that we have multiple sequences of iterations here of matrix multiply activation function. I will say this as a weakness. So I like R. R is great for doing data analysis. It's customized for doing data analysis, and so it tends to be very strong at it. But Python has better packages for deep learning. That's just where people who are doing deep learning and the industry tools are being developed in Python. So if you're going to do a lot of deep learning, Python is you should be using Python instead of or in combination with R. Another vocabulary word here is that the size and assumed sparsity. So we saw sparsity in the last discussion. Sparsity is the structure of zeros. So which entries are assumed to be zero of these A matrices are called the network's architecture. So basically just the structure of these A matrices give you the network's architecture. There's a lot of dials to turn in there as far as what should be the shape of these A matrices. Should you have zero entries? Should you not have zero entries? This is a big area of research, and there's lots of different variations of neural networks depending on how you structure these A matrices. Okay, how do we fit a neural network? Well, actually, we've seen how to do it in the context of linear regression, and that is similar to linear regression. We will minimize mean squared error. So instead of minimizing in a single vector beta, now we are minimizing in these L matrices A1 through AL. Okay, so the goal is to minimize this expression, and this again, of course, is mean squared error. This is the mean squared error between y and our prediction. Okay. To ease my notation a little bit, so I don't have to write this as my output every time, I'm going to let FA sub x, or so F sub A of x, this is going to be the output of my neural network. So I'm going to combine these matrices in some big A, and then say FA xi is my prediction of y given an input xi. Okay. Minimizing this expression can be computationally intensive. And in particular, it's one of the reasons that neural networks have been around since the late 80s, as we mentioned, but they weren't able to take off, is because of hardware limitations. And so this can be difficult to minimize in general. There is because of the sequence of linear operations, there is some mathematical simplicity to this operation, but in general, this can be difficult and sometimes takes fancy hardware to do it well. If you have shallow networks, you can often you can also fit neural networks on your laptop, and we will demonstrate that in a little bit. So what can we not use now that we're not working with linear models anymore? Well, we can't use malloc. The reason we can't use malloc is, remember the assumptions there. They relied very heavily on this this linear structure between y and x, the assumption of constant variance, so on and so forth. This was a specific tool for linear regression. We can't use diagnostic plots anymore, since we can't show that the mean zero assumptions should give us mean zero assumption in the residuals or constant variance in the residuals. The ability to compute variances, residuals, etc., a variance of the estimator, beta hat, or the variance of the residuals, we lose this ability because of this complicated relationship between our input and our prediction. Okay. We're losing VIFs because we can't compute variances. We're losing the results that rely on beta hat or y hat being Gaussian. So with this third assumption, of Gaussian errors and independence across observations, we develop things like the t-test and the f-test. We can't use them anymore because we don't have the structure permitted to for these tools to hold. Confidence and prediction intervals, these also come out of this third assumption, which we can't show that beta hat should be Gaussian. But we can use some tools, and in particular the maximum likelihood tools. So when introducing maximum likelihood tools, I said, well, in general, they tend to be preferable to the tools that are specific for linear regression because they're more applicable outside of this case. And in particular, this is useful in this context, some of these maximum likelihood tools, because we can show that this MSE minimizer is the maximum likelihood estimator when y is some function. So this is the output of my neural network. What this says is the relationship between y and x is you feed x into this neural network, you get y plus some noise epsilon. And so the selection of A, which minimizes mean squared error, is the maximum likelihood estimator when epsilon is distributed normally mean zero variance sigma squared. And this derivation actually works very similar to how we saw it in linear regression case. You can show that the maximum likelihood estimator of the A's is equal to this expression. You take the log likelihood, instead of maximizing the log likelihood, you minimize its negative, and you end up with some expression that looks like this. Okay. So in that vein, maximum likelihood tools are still valid. AIC, BIC, stepwise variable selection with these tools. These rely on maximum likelihood estimation under the hood. Because training takes usually takes a long time in neural networks, it's not practical to train many models using this stepwise selection because you have to train and retrain at every step. The theory works, but it's not practical when your training takes longer. The log likelihood ratio test is still valid, again, assuming you can justify this claim here. The train set test set paradigm, doing cross-validation, is still valid. This is one of the things that has been around the longest in the course. The reason is that it is sort of more fundamental in the sense that when your assumptions degrade, as we see in this application, we can still always use train set test set. RMSE, mean absolute deviation, R squared, we consider them all just as before. Principal component analysis, using eigendecomposition to detect multicollinearity. These are still applicable. We can look at the predictors, see where which directions in predictor space have high variance. That's an indication that There's a lot going on in those directions, and we might find more effective predictors there. We can still do two-norm penalization of the mean squared error. Okay, this is similar to ridge, right? In the ridge estimator, we add a squared two-norm penalty to the mean squared estimate to the mean squared error, and that allows us to reduce the variance of our estimate. So when we have multicollinearity concerns, we can add this two-norm penalty. We can still add the two-norm penalty and the multicollinearity concerns because we don't have access to a VIF. Will have to be diagnosed by PCA and the eigendecomposition instead. And then we can still do one norm penalization for variable selection as in the lasso. We can add a one norm penalty to our mean squared error to induce some sparsity. Okay. How do we do neural networks in R? There's many packages. Neural net is one that I like in particular because it has nice graphics to display what's going on, and I'll show you those in a little bit. Keras is another popular one in R, though as I say, if you're doing a lot of training of neural networks, Python is superior. Okay, in Python, I'll just mention PyTorch is the package that I prefer. Some folks prefer TensorFlow. Keras has an interface for TensorFlow, and many people use that. PyTorch is, I think, very nice because it's the closest to writing down an equation and being able to just put that equation into Python. The initial learning curve for many of these packages which are dedicated to deep learning can be very steep because there's a lot of dials that you can turn when you're constructing a neural network. So in particular, choosing the sigma function, this activation function is one we know of so far. Choosing the architecture of the neural network, it's just there quickly becomes an infinite amount of ways that you can make minor manipulations, and so having all that flexibility, it takes some acquainting yourself with the software tools to do it. Okay, so let's turn to R for a little bit, and I will introduce how to use this neural net package in R. So I'm going to be looking at the data set from the first data analysis project. That is the bike data. Okay, so I'm going to load up the neural net package, install it if you haven't. I'm going to read in this bike data, which is, of course, we're predicting the number of the number of bicycle rentals using attributes of the day, attributes of the weather in which the bicycles were being rented. Okay. So we have all these call names. This is, for example, again, the season, the year, the month, and the variable of interest was count. So just because I want to illustrate these tools, start simple, I'm going to only use temp as a predictor. So I'm going to have only a single predictor, which is going to be temp. Okay. This is just the simplest, and it allows me to create some graphics to illustrate a little bit what's going on. I'm going to scale temp and count. This is important when training a neural network, that these variables be scaled. Much more important than it is in the least squares estimator setting. We won't talk about how the optimization is done, but in general it's more complex, and it benefits from scaling your predictors and your response variable. I'm going to build a design matrix X. Okay, and then I'm going to make some training and testing sets. And I'm going to build a linear model. Okay, so this is a linear model predicting count from everything in my training matrix, and my training matrix is so my training matrix only has these two variables in it, which I've already selected them. And this is just too much to scroll through, but this is let me see here. Oh, of course, I subselected here. So I subselected just for temp and count variables, so that's why I only have two columns here. Okay, so I built a linear model. So this is count predicted from everything, and by everything, because I'm just working with the temp variable, this is just going to build a linear model which predicts count from temperature. Okay, going to look at this model, and I see simple linear regression model, intercept, temperature. Okay, so I can build a neural network with no hidden layer. Okay, remember I said this before, but a neural network with no hidden layers, that is with just one layer, is a linear model. Okay, or I can build a neural network with, for example, here I have 2 hidden layers, each of which are size 2. So what's happening is I have no hidden layers. I'll just break down this command. I'm calling the neural net function from the neural net package, predicting count from, again, everything in this data set, which everything in this data set is, of course, just temp. I have no hidden layers. I'm specifying a linear output. This means that I don't apply an activation function in my last layer. And then step max is related to the optimization of the mean squared error objective. So here's the deep neural network where I have 2 hidden layers here. Okay, and you notice that it took just a moment for it to run. This is to be expected, and this again is my so this is again the coefficients of my simple linear regression model. The reason that I pull them up is to compare them with what happened with my shallow neural network. So let's look here, and we see this is a graphical representation of a neural network that the neural net package will build. So what we have is a predictor, okay, and then we have this arrow represents a coefficient. This black arrow represents a coefficient to be estimated. This 1 is saying we have an intercept term, and that intercept term, that 1, is multiplied by 0.03316. So this represents an intercept term. This is a coefficient. And so this is, again, coming from the neural net package. This is the neural network with no hidden layers. And we see that, unsurprisingly, a neural network with no hidden layers has the same intercept and the same coefficient as the output of the simple linear regression model. Okay, so we see these values are exactly the same. This is saying take temperature, multiply it by 0.63, and then take this constant 1, multiply it by 0.033, and when you add those together, you get your prediction of the count variable. Okay, so these arrows are showing, these black arrows are multiplying coefficients, these blue arrows are intercepts, and when they come together into a node, we add them together. And so let's look at a plot of the deeper network. Let me get rid of that. So here's the deep network that I built, and it's not, by modern standards, this is definitely not deep, but it has multiple hidden layers, and so this is not the shallow network that we were working with, that we could be working with, right? So it has more flexibility. I think that if you claim to be doing deep learning because you built this simple model, people would say, oh, this is not really deep learning, but it's capturing all the important bits, just in a simple example. Okay, so what's happening is, again, just following through the plot here. So we have temperature as a predictor, and then we have these 2 hidden layers, and each one of these hidden layers, so what's happening is temp is multiplied by 0.85, and going into this hidden layer with an intercept of negative 0.2. Here, temp is multiplied by 47, and goes into this hidden layer, so this node of the hidden layer, with an intercept of 25, and then goes to the next hidden layer. So the output of this hidden layer, there's an activation function applied here, and then it's passed to this node, multiplying by a coefficient along the way. Same here and same here. So what's happening is, again, we have the output, we have a nonlinear function being applied, and then we're multiplying each one of these outputs by the appropriate coefficient on this arc here. Okay? We can just keep track of the intercepts happening at each node as well. Okay, and then lastly, at the second hidden layer, again we apply the activation function. That's a nonlinearity here, and then we multiply the outputs by these certain coefficients, along with adding this intercept term here to get our final prediction. So it's harder to see what's going on, right? One of the benefits of using the simple linear model, if I look over here, we see temp has a positive coefficient, which means that we can interpret this and say, as temperature increases, our prediction of count is going to increase. But when you see all this going on, it's harder to tell. And there are some tools for interpreting what's going on in a neural network, but you can see that the problem becomes much more difficult. And that is one drawback of using them, is that you lose some simplicity. In some cases, losing that simplicity of interpretation is worth it when you can have better predictions, but it's just something to acknowledge. So what I'm going to do next is I'm going to predict using the deep neural network and using the simple linear regression model, or i.e. the shallow net, because we just showed that they were the same thing. I'm going to predict on the test set. I'm also going to compute the mean squared error of both models just to see which one performed better. So this is the residuals for the neural network. This is the residuals for the linear model. That is the simple linear model. And then I'm going to compute the mean of their squared residuals for both of them to give me the mean squared error. I see the mean of the neural network is 0.65. Sorry, the MSE of the neural network is 0.65, whereas the MSE for the linear model is 0.64. Okay, so here we see, and this depends on the train test split, and also actually the training itself is random, but here we see on the testing set, the neural network has performed a little worse. Okay, I'll say that most of the times when I run through this, the neural network is performing slightly better, but not far and away better. Let's just run this again and I'll see. Oops. Okay, so this is more, again, just having run through this a few times. You know how the training and testing sets work, but this is the neural network here. We have 0.1 MSE less for the neural network than for the linear model. This seems to be, having run this a few times, this seems to be a little more typical of the performance difference between the two, but I think we just got a little unlucky with that train test split, but it's worth acknowledging that it's not by far and away that the neural network is beating the simple linear model in this application. Okay, so I'm going to plot then the output here. So I'm going to plot this is standardized temperature and standardized count, and then I'm going to plot the predictions in both settings. So here's, of course, the predictions for the simple linear regression model. We have some problems here, as many of you noted in your data analysis project, that we are overestimating in these when it's cold out, we overestimate the number of bike rentals, and when it's very hot out, we are underestimating. Okay. But then I'm going to plot also in red here the predictions of the neural network. Okay, and so here we see some definite nonlinear structure. So we have this input here, right, of course, and then we sort of see these couple of steps. So this is, it's very cold, not that many people are renting. We see some increases here, and I think you can argue, you can look at this trend and say, is this a better fit? Perhaps not. But it's interesting nonetheless that when you introduce this nonlinearity, this big sequence of layers that we saw here. So this was our deep neural network when we had these two hidden layers, is producing some nonlinear relationship between temperature and count, and here is the relationship. Okay, so it's doing well in the sense that I think that this is a good call, this way that this sort of flattens out here in this area. And the linear model doesn't have the ability to do that. If we added enough polynomial terms, we could approximate this sort of curvature, but regardless, we can just see what's happening in the relationship between x and y. It is nonlinear. We didn't have to go search for transformations manually. They were found. This relationship was captured for us. Okay. So that's, again, a small example, but one that I wanted to mention. Okay, so I'll conclude this lecture by just reminding us of where we've been. So neural networks, they're extensions of linear models. They're similar to linear models in that we apply these linear transformations, but not similar, and we depart from linear models in the sense that we apply this nonlinear activation function in between each layer, and we introduce nonlinearity. What's good about them is that they can model more flexible relationships between x and y, and it does it automatically, right? We didn't have to find good transformations in that relationship between temperature and byte count, right? The number of bicycles rented. So you can model more flexible relationships, and you can find transformations automatically, in particular when it's difficult to find those relationships by eye. Some drawbacks is that the theory for linear models is rock solid, right? We were able to do a lot with them, starting with, for example, the truth plus error representation, all of the theory we were able to show for that in terms of the expected behavior of linear models given certain model assumptions. The relationship between model assumptions and outputs is not as well understood, and in some sense, we don't have the strong tools that we had before, so that's one weakness. In terms of inference, so relating qualitatively the relationship between inputs and outputs, it's harder to do, and they're not as well understood. So if you want to do inference, a lot of times linear models are your best tools because of that relationship, of the ability to do things like hypothesis tests. We don't have that ability in neural networks. Another con, we haven't spent a lot of time talking about this, but it requires a large set of training data to be able to work accurately. This makes sense, but if I jump back to the formula here, some ways back, but the relationship between input x and output, we have many matrices we need to estimate. So the number of parameters here, and especially in the modern case of modern machine learning, there can be millions of parameters here for state-of-the-art networks, and it requires many data sets. I think ResNet is a very popular network architecture, and it has around 1 million parameters. So having many parameters to estimate, this obviously makes sense that we would require a large amount of data to do so, to estimate those numbers reliably. If you don't have a large amount of data, if you try and throw a neural network at a problem, you can do worse than linear regression. Okay. Also, you require, for especially training big networks, you require dedicated computational resources. This can be expensive, whereas linear models, we've been able to fit linear models on our laptops all class. They are suited for prediction. It is difficult to interpret them. There are some dedicated tools for interpreting them, which we won't talk about, but they're more complicated. They're not as reliable as what we've done for linear models, and in general, neural networks should be used for prediction and not inference. I'll say my opinion here. So only in very rare cases would I not use a neural network. So the reason is that right, we have some of this idea of when we're fitting linear models, it's hard to know when we're done. We're building a linear model, we're making a tweak, we're seeing if we have an improvement, so on and so forth. And so a minimal modeling with neural networks allows me to ask a question, which is basically, does nonlinearity benefit me, right? If I have some basic structure which I found in a linear model, I feed those predictors into a neural network, which I make maybe shallow, for example, and do I see improvements here, right? That gives me a hint that I've left something on the table that the neural network is able to pick up on that I'm not. If I don't have enough data to build a neural network, I don't have enough data, and that's okay. But because linear models are a special case of a very simple neural network, I can just add in, for example, one hidden layer and see what happens. And this is a way to just see, is nonlinearity benefiting my problem? And so, yeah, so if I see, again, big improvements between the neural network and the linear model, then I say, well, probably missed something with my linear model, or maybe there's some nonlinearity in there, which is really important in the relationship between x and y. If the performance is not similar, right? So if the performance is similar between the neural net and the linear model, this is a hint that nonlinearity is not benefiting you. If you found good transformations, so on and so forth, it's a hint that you're doing something right. But if the neural network is better, how much better is it? They should always be better because, of course, a linear model is a very simple neural network with no hidden layers. So you should at least be able to attain the performance of your linear model. And then you can just add a little bit of layers to see if there's an improvement. So neural networks are never going to be hands down worse because you can scale the simplicity of the neural net until it is a linear model, of course. And then I'll just present. So in my discussion working with research sponsors, I'll say, okay, I have a model on one hand, which is more interpretable. But on the other hand, I have a model which is more of a black box, which performs X% better. Which do you prefer, right? And instead of, for me, trying to make a decision as an analyst, a lot of times I find that research sponsors will say, well, we want this black box model, even though it's only 1% better. That prediction performance is very important to us. Or, as I say, maybe sometimes people are just happy to be able to say, we're using a fancy neural network, maybe without understanding the details of what exactly that means, and that leads them to choose more complicated models. I have no idea, but this is my workflow, and this is what I recommend you do as well, which is you can rely on the core tool set that we built in this course and do some minimal modeling with neural networks as a point of comparison, and present two models and say, here's what I have, which do you believe would be better for your application? Okay, so that's all I have about neural networks. I hope you enjoyed this lecture, and I hope you enjoyed the class. Thanks for sticking through it, and I hope to see folks around.